Okay. Dear students, I welcome you all for this invited talk lecture by Pelin ANGIN, and the profile of the lecture will be introduced by our Professor Dr. Sukmar Garu. Now I invite Dr. Sukmar Garu to uh, read out the brief bio of the invited.
Good afternoon, all. It is my privilege to introduce Dr. Pelin Angin is an associate professor in the Department of Computer Engineering at Middle East Technical University, Ankara, Turkey. She received her BS in Computer Engineering from Bilkent University and her PhD in Computer Science from Purdue University, USA. Before joining this university, she served as a visiting assistant professor and postdoctoral research associate at Purdue University. Her research interests include cloud computing, cloud security, Internet of Things, security, IoT, distributed systems, blockchain technologies, cyber security, mobile cloud computing, and privacy preserving intelligent systems. She has published extensively in leading international journals and conferences and actively contributes to the global research community through editorial and technical program committee roles. The organizers of CIGAI 2026 conference are delighted to welcome Dr. Pelin Angin as an invited speaker. Her keynotes will share valuable insights into container security for 5G and beyond. Thank you, madam. Thank you. Thank you all.
Thank you very much. I'd like to thank the organizers very much for inviting me. It's very special to be giving this talk today. Shall I go ahead and start? If everybody
Yes, madam, please.
Could you turn sharing on? I'm not able to share my screen right now.
Madam, now once you check, you will get the option of sharing.
Okay, thank you. I hope you can all see my slides right now. If yes, I'll just go ahead and get started. Okay. So today we'll be talking about a very important topic for actually 5G and beyond networks, but also for other fields that shape our lives today. So we're gonna get started with an introduction of what the promises that are made by 5G and beyond networks to us are, and we'll talk about how SDN is related, how software-defined networks are related to that issue, as well as how cloud computing, and container technologies are related. And then we're going to go into the security of these technologies, which will very much shape the security of 5G and beyond networks. So this picture might be familiar to a lot of you. When they made promises to us about what 5G networks would deliver, they focused on 3 use cases, basically. What they said was 5G networks would be supporting massive machine type communications with low data rates, high device density, and latency, as well as low power. That was one of the promises made. The other promise was enhanced mobile broadband, which would allow us to get very high speeds for a lot of applications that needed them. And the other promise was ultra reliable and low latency communications, which would allow us to get very low latency for applications that needed them again. So today, 5G networks have been deployed in a lot of places in the whole world. But when they were first deployed, when they were first launched in some places in the world, they were not really able to actualize these promises. So we were expecting a lot from 5G networks, but when they were launched in some places, we were a little disappointed, basically. And that really is related to the unpreparedness, I would say, of the underlying technology and the background, the infrastructure, as well as the software background that needed to run them. And this talk will be very much about what other technologies we'll need to bring in, or how we need to improve the existing technologies to achieve the promises made by 5G and beyond. So, we're using 5G networks right now, but they will evolve into 6G networks, maybe 7G networks, and this evolution will continue. And you cannot really draw very clear-cut lines between these technologies. So you might see 6G coming up anytime soon, basically. So these promises actually relied on, when people were designing 5G networks, they relied on 2 key enablers to achieve all of these promises made by them. The first was software-defined networking and network functions virtualization that really comes along with it. And the second key technology was network slicing. Today, we're going to focus more on software-defined networking and network functions virtualization and see how containers are very much related to these technologies. But of course, network slicing, again, is a very important concept for achieving the high performance that was promised by 5G networks. So if we look at the software-defined networks architecture, which is actually quite different from the legacy networks which we're using still in some places. Software-defined networks is not a very new concept. So this concept has existed at least for the past 10 years or more. But they are being increasingly adopted in a lot of places, and I think they will have to replace legacy networks completely to achieve the high performance guarantees that we require for a lot of applications. So what's different between a legacy network and a software-defined network architecture is that you are separating the control and data planes from each other. So what that means is, in our legacy networks, we had routers which were much more capable than the routers that we have in software-defined networks. So basically, your router would be running the routing algorithms at the data plane layer, and there was no separation between the control plane and the data plane. In software-defined networks, we're separating those two planes from each other. And we're putting all of the intelligence in the control plane, actually. So we're softwareizing all the intelligence rather than having intelligent routers at the data plane. So now these routers, which are responsible for routing our network packets to their destination, are very simple. They do not have any smartness in them, let's say. They just keep tables for deciding when a packet comes where to route it, but they do not do things like running advanced algorithms, for example, for deciding how to route those packets. So that responsibility lies completely on the control plane now. And the control plane consists of software, actually, what we call controller. And that controller basically oversees the whole network. It looks at the layer above from the top, and it sees the whole network to make much more intelligent decisions regarding how the routing is to be performed. And at the top layer, of course, we have applications that interact with this controller through the northbound API. And the communication between the control plane and the data plane is provided using the southbound API. So the most popular protocol for the southbound API has been the OpenFlow protocol ever since the software-defined networks concept was introduced. And at the control plane, we have a variety of controller choices. So we have POX, Open Daylight, Open Contrail, ONOS, and the list goes on. So people could have come up with new controllers with different functionality at the control plane. And we have a bunch of software-defined network and business applications running at our top layer, basically. So the software-defined network architecture is a key enabler for 5G and beyond networks because of the high flexibility and scalability needs of 5G. So to achieve all of those promises of high performance, ultra reliable, low latency, massive machine type communications, we need very high flexibility and scalability in our networks. So we cannot really rely on an admin, for example, an IT admin to manually configure the network for us to achieve all that flexibility and scalability needs. Everything needs to happen very quickly. Everything needs to happen in a very scalable manner because your network needs to be elastic. It needs to be able to adapt to changing conditions really fast. So this is what the SDN-based 5G architecture looks like. Again, so we have management tools, business applications, and other applications at the application layer. We have controllers. So we talked about a single controller in the previous picture, which means centralized control instead of distributed control. But of course, you do not want to rely on a single controller to do the whole work, right? Because if that single controller becomes a single point of failure, it could be attacked and the whole network could be down, right? So that is why you will most likely want to replicate your controllers across multiple servers at this layer. And at the infrastructure layer, or what we call the data plane, again, we have these hardware for routing. We have the backbone network, the software-defined core network. And attached to that, we have the backhaul links, which are attached to software-defined radio networks, basically. And these are like the base stations, for example. So actually, software-defined networking itself is a great enabler for network security because it allows us to more easily collect network usage information. So if we go back to this picture, for example, if you were relying on these individual routers, if you were relying on the data plane to collect usage information, that would be very much decentralized, and it would be very difficult to make informed decisions about what's going on in your whole network, right? So instead of that, we have controllers which are collecting all that information from the data plane. And the information collected by the controllers are relayed to the layer above, of course, the application layer, where we could run a lot of tools like anomaly detection or performance evaluation for your network. So we have a much more global visibility of the network in SDN. So because it makes it easier to collect network usage information, it makes it easier for designing algorithms that detect attacks in our network too. So SDN enables us to enforce policies in an easier manner too. So we have improved policy enforcement that comes with SDN, and improve anomaly detection too. So we can see the whole network and can detect anomalies in a much easier manner. And it's not only about detecting, of course. So once you detect these changes in your network that could be pointing to anomalies, it does not have to be attacks either. So it could be anomalies that are caused by network usage too. And you want to be able to detect them as soon as possible so you provide uninterrupted service to your clients. So when SDN detects these anomalies, it will be able to provide an intelligent response through selective blocking of malicious traffic too. So SDN, of course, is not a passive entity. The controller here is not a passive entity. It processes all that information it gathers from the network, and it acts upon that information by doing things like maybe diverting traffic, certain traffic, to different places, or blocking certain traffic if it suspects that there is something malicious in it, like a denial of service attack, for example. So, of course, it's possible to attack SDN in a lot of ways too, at different points. So one of those points is the data plane. So an attacker could try to attack these links between different routers, or they could try to attack the routers themselves. These routers all have flow tables, and they could try to change the information in those flow tables. They could try attacking the communication between the control plane and the data plane. They could try to attack the controller itself. So that intelligent controller where all the routing algorithms are running is one of the places that are hot targets for attackers, because if you destroy the control plane, you destroy the whole network. They could try to attack the API between the control plane and the applications to disrupt their communication, or result in faulty communication between them. And again, they could try to attack the applications running on the application layer. So this was one of the most popular attacks when SDN started. Basically, you have, and this happens a lot if you have especially a single controller. So what happens when your routers do not know how to route a packet if they have not seen any instances, any similar instances of that packet before? So if they do not know how to route that packet, they will be asking the controller how to route it. So if their flow table does not have any entries related to that packet when they receive it, they will send a packet in message to the SDN controller, and the SDN controller will respond back to them using a packet out message. So if you send enough of these messages, enough of these different messages, actually, different packet routing messages, one of the things you can do, of course, is to make the controller put a lot of load on the controller so that it cannot respond to any more queries. And another thing, of course, you can do is to make this table to overflow. So it does not know how to route the packets that it received before, for example. So this is more like a denial of service attack on the SDN structure. And it's only one of the attacks that could be performed, of course. So we'll jump to an introduction, a very small background on cloud computing here, and see how it's related to the case we're talking about here. So cloud computing has made some promises to us too, right? So it promises to provide rapid elasticity, which means so when you need more resources, it will be able to scale up and give you more resources. And when you need less resources, it will be able to scale down, right? So it provides on-demand self-service so that you do not have to keep those resources at all times, but you will be provided resources when you need them. It promises broad network access, it promises resource pooling, and it promises measured service. So these are all promises of cloud computing that are very important for 5G and beyond networks too, as we'll discuss more later. And so the most important feature of cloud computing is actually what we call agility. So if you look at Oxford Dictionary, agility is defined as the ability to move quickly and easily, right? So when we apply that to cloud agility, that really means rapid provisioning of computer resources. And it's not only new compute instances, it's also networking and storage provided in minutes instead of weeks taken by your IT department, for example, when the configuration is done manually. And it also means rapid business response to changing conditions. So which means a shortened time to market. So of course, to provide these agility features, cloud faces a lot of challenges too. So when cloud computing started many years ago, it was really mostly based on virtual machines, right? So if you have ever used the services of any cloud provider like Amazon, for example, Amazon Web Services, when you wanted to launch a virtual machine, you would need to wait for a few minutes, right? Because so that builds a whole machine, a whole virtual machine with a guest operating system in it. And it takes a few minutes for that virtual machine to be up and running, basically. So that goes a little against the agility we need from cloud computing. So we need less resource consumption than virtual machines. We need something lighter, more lightweight, and more portable, so we can quickly deploy it for increased agility, right? So again, geographically distributed mission-critical applications may suffer from limitations in network quality of service, and that means limited responsiveness to changes. And again, when we talk about cloud computing resources from the perspective of networks like 5G and beyond, provisioning networks to deliver optimal paths between new applications and users can take days, hours, or days in the worst case. So enforcement of policies in networks involves a complex architecture, of course. So if you're building your whole network using cloud computing resources, that's not an easy task. And you need to really be careful in the configurations that you're making so that you can enforce your policies, especially if we're looking at it from a security perspective. Your security policies, their enforcement is not that easy, right? So, and again, enterprises, of course, have limited control over cloud operations too. So these are the challenges that are faced by existing cloud systems, or let's say legacy cloud systems. And so that is why actually, instead of using virtual machines, people started moving towards using containers, which are much more lightweight. We will talk about containers in a little more detail later. But containers are basically a component of cloud agility. So they allow rapid service deployment. They allow lightweight, high performance components, easy service migration, and high service uptime. So a concept that is very much related to containers, because microservices mostly consist of containers running on them, is basically microservices allow us to create flexible service compositions. And they provide interoperability. We're going to talk about microservices in more detail too. And of course, the other component of cloud agility is SDN and NFV. So actually, you will see that this goes both ways. So in order to provide agility in cloud computing, you need your cloud infrastructure running on software-defined networks. But to be able to build software-defined networks in an agile manner, you will need cloud computing resources. So there is a two-way link between them. And software-defined networks and network functions virtualization, which means you're basically softwareizing all of your network functions. They provide rapid network resource provisioning, easy network policy enforcement, rapid network maintenance, and quick network failure recovery, basically. Okay, so let's talk more about what a container is now. A container is a lightweight structure in which an application can be stored, carried, and run on a compatible operating system. So here in this definition, this compatible operating system part is quite important, because this really means that a container does not carry its own operating system. That is the basic difference between a virtual machine and a container. So a container does not encapsulate a guest operating system, which a virtual machine does. And that's what makes it so much lightweight. So a container encapsulates application logic components provisioned with minimal resources. And there is no need for embedding an operating system into it. So it runs on a compatible operating system. And you can place it on any host without special configuration. So when we're talking about containers, we're talking about virtualization at the operating system level rather than hypervisor level, which is the case in virtual machines. So the required components for running a container is a compatible operating system, a runtime compatible with containers to run, and a platform to manage applications. As well as, so if you need to orchestrate different components, if you need to make different components talk to each other, you'll also need a tool for orchestrating containers their management, networking, and security. So in this picture, we see the difference between virtual machines and containers in a more clear manner. So on the left, we see virtual machines, and you see that in the virtual machines, you have a whole guest operating system. And having this whole guest operating system is what really makes the launching of virtual machines and their runtime, the whole runtime, much more cumbersome. So basically, everything that is all the applications running in your virtual machine here, for example, will need to, when they make calls to reach the infrastructure, those calls will need to go through this guest operating system and the hypervisor. But in a container, you just have your application and the binaries or libraries that are needed to run that application. All of these run on a container engine. There is a single host operating system, and all the calls that they make will just need to go through this host operating system. So there is no going through a guest operating system, and that makes containers much more lightweight. But one thing you will notice here, of course, is that when we talk about virtual machines, we see that there is a stronger isolation between them because each has its own guest operating system. So we're not talking about that much isolation when we're talking about containers. And that isolation, as we'll discuss later, will be very important for security, of course. So again, the advantages of containers or virtual machines is improved performance, reduced application size, increased stability, and reduced footprint. And if we want to look at the history of containers very quickly, they have their roots in the Linux world. They have a lot of features based on the Linux kernel. And early containers included things like FreeBSD jails, Oracle Solaris zones. But they became more popular when Google got involved in their development, basically, as early as 2006, actually. So Google built an entire data center architecture based on containers, and they used Kubernetes, which is a very popular container orchestration platform still today, for their container and cluster management. So Docker is a very popular container today as well. So it got increased traction in the container world. It was started as an open source project to build containerized microservices in 2013, which was followed by their company. And then Linux containers came along as a major competitor for Docker. So here's what Docker looks like, what the Docker operation looks like. Basically, we have what we call images. So you can think of this, a container image, as basically an application along with the libraries that it needs to run. And these images, container images, are stored in container image repositories. So whenever you want to use an image, you pull it from that repository, you basically start running it. So in Docker images, you have what we call read-write layers. So you have you start with a basic image, and all the changes that you make to that image are layered on top of that image. Basically, it's like an onion. So as you peel, you get down to the inside of the original image. So you have these read-write layers on top. So I'm not going to talk about this in detail, but basically, whenever you want to run, create a new image, You just pull that image from the repository using your container orchestration platform. You just have it built and start running. So it is that easy, basically. And it takes a very short time to do this whole process. So how do containers provide agility? They share the same operating system, which means less resource consumption, increased efficiency, fast application upload, and no downtime during application updates. This is very important too. So you don't want to have any downtime when you're reconfiguring your network, for example, right? That is why containers help a lot when we want to achieve the promises made by these fast networks. And containers also allow applications to be separated from the underlying infrastructure, which means increased portability. So you can port your containers anywhere as long as there is a compatible operating system there. And this has potential security benefits. So let's talk a little about microservices. Microservices really actually have their roots back in service-oriented architecture. Basically, in microservices, you do not have applications that are cumbersome, which have a lot of functionality in them. You split your applications into smaller functionalities. And you make those services talk to each other to achieve your bigger functionality, basically. So this is what the difference between monolithic applications, where you put all the functionality in the same place, and microservices, where you split up that functionality, looks like. Microservices are very important for agility as well, because whenever you want to make a change in your application, for example, you do not have to change the whole application. You just change its different parts independently, and your whole application still keeps running while you're making changes in that small part. So microservices, of course, are used a lot in a lot of places today. They're independently deployable. They have more explicit component interfaces, and there's decreased coupling between components. So you can continuously deliver them. That is what enables them to provide resilience against failures, as you're able to monitor each of them separately. And a lot of the web services that you will see today are built upon microservices. So microservices architecture is used by Amazon, Netflix, Uber, eBay, and many other companies, basically. So why mention microservices? Because the whole web today, most of the web today is built upon microservices, and the same goes for the cloud infrastructure that software-defined networks are using too. So all those applications that are running there that are used for keeping your network up and running are built on the microservices architecture, actually. And microservices use containers to provide those functionalities. So the services in microservices are mostly running on containers. Okay, so we talked about a lot of advantages of containers, of course, but of course there are some problems with containers too. So the proliferation of container networks has revealed the potential of exposing these networks to many cyber attacks caused by the malicious capture of endpoints like IoT devices. And as we discussed before, containers do not provide a strong isolation as virtual machines do. So that makes them more prone to attacks. And software-defined container networks are actually a fairly new concept. There is not a lot of studies on this topic. And that makes automated attack detection and prevention for these networks not widely available yet. So if you have your infrastructure running on container networks, attackers are coming up with new ways to attack those networks every day. So here are some real incidents of attacks that were run against containers. So for example, in 2021, research found that adversaries could detect a misconfigured container with an average of 5 hours. And if you find a misconfigured container, then you try to attack it, of course. Container networks have different types of attacks that we're not used to from legacy networks that they're vulnerable against. And some of those attacks include things like container escape attacks, for example. So let's see a bigger picture of that here. So there are many attack vectors that you can use to attack containers. Of course, one of them is insecure networking. Another type is vulnerable code exploits. So you can perform vulnerable code exploit attacks against the host application, but also the container orchestrator on which that host application is running. And we talked about container escapes. So let's say you have multiple containers running on the same infrastructure. And if one of those containers has a vulnerable image, and that image is captured by attackers, and if the attacker is able to escalate its privileges to admin level, it might be able to start controlling the other containers running on that same infrastructure too. So that's a very actually dangerous attack for all of the containers running on that platform. You could have badly configured container images, compromised container images. So that is why you need to be very careful when you pull up an image from a container image repository and you deploy and start running it on your platform. So that is what led our research group to start working on a container security proposal for basically container networks and its applications to 5G. What we proposed in this work had a lot of different components, of course, and the description of each of these and the results that we achieved goes a little beyond the limits of our talk today, but I'll try to explain it briefly. Basically, again, here we have our containers which are communicating with each other through our data layer routers or switches. And of course, those switches, we pull information from those switches using and relay it to our controller layer. And the controller relays that information to our application layer, which has components for intelligently classifying the information it received from all the layers down, which is by using machine learning and deep learning algorithms. And it has a mitigation module, which is basically for allowing the controller to perform security policy updates based on the information that was extracted by this traffic classification and intelligence module. So what kinds of security updates could it be? It could be, for example, if it has detected that there is a possible denial of service attack originating from a certain IP address, it could block that IP address completely. So blocking an IP address really means you will need to send a flow rule through the control layer to the data plane here, so that when the routers here see traffic originating from that IP address, they will block it completely. They will not allow that traffic to pass. And this whole structure tries to achieve that in a very agile manner, basically in a very real-time manner, so that these policy updates are propagated all the way down, so that your network is instantly reconfigured, basically. And of course, so whenever we talk about machine learning and deep learning, we need data, right? So to be able to build such a system, you need to give it some examples of attacks against containers. We did this in an isolated manner. Of course, we ran our attacks in the lab environment to collect some data. And of course, so that data collection process is kind of never ending, right? So you get new types of attacks, you need to collect new data that is used for modeling those attacks. And the more data you need, the more labor you need to label that data. So it's better if you're able to run, create models that are able to run, like give you good results using little data, right? And that's where few-shot learning comes into play. So we tried few-shot learning algorithms to build models that are capable of distinguishing between different classes of attacks against containers by using only a few samples for each attack. And then comes in the part where you need, so you cannot rely completely on machine learning or deep learning algorithms to correctly classify all of the instances in your network. So you need to keep humans in the loop to provide feedback about the results of those models, right? So that was the last part of our project, where we had an active learning component which provided feedback to the algorithm to improve its performance in doing the classification. There are some container security studies in the literature, but there is not a lot of them still. So I think people are not really aware of the importance of container security yet. And of course, there is a wide literature of studies in the security, cybersecurity topic, but container security has not been focused on a lot. And that is why I think container security will be one of the most promising fields of research to pursue a career in. So when we started our container security studies, we started by analyzing some existing attacks against containers by performing a search on common vulnerabilities and exposures database. And that resulted in a lot of different types of attacks, actually. So some of you who are in the field of security would be familiar with MITRE's matrices for analyzing different types of attacks. And when we looked at attacks on containers, we saw that there are different types of attacks under each of these topics. So initial access, execution, persistence, privilege escalation, defense evasion, credential access, discovery, and impact. So people have already created a lot of attacks under each of these categories, basically. And what we did to implement these attacks was to use the CIGAI engine, Web Application Vulnerability Scanner. So we tried to find YAML templates for each of these different attacks. And I think we were able to run 19 of them in the end. And so our experimental pipeline consisted of, so basically you run these attacks and you need to collect some data from your system to detect those attacks, right? So what we did was to use two sources of information to detect attacks against containers. The first source was network traces, which we collected using TCP dump. And the other source was the SysTick tool, which allowed us to collect system call information during the runtime of those containers. And then we extracted some features from all that information that we gathered, and we input those into our machine learning models and try to see if there is an anomaly or not in the system. So again, our data set consists of network flow and system call data. We initially started with some machine learning algorithms, and our purpose here was to only detect anomalies, so not distinguish between different types of attacks, just see if there's an anomaly or not. And we used these 4 algorithms for that purpose. Our network features consisted of this list, and whenever you do network intrusion detection research, all of the data sets will have similar features to these actually. And our results show that actually network flow data, so the results actually seem to be quite successful. So we were able to achieve a high anomaly detection accuracy in these experiments that we did. But we also see that network flow data was more successful than system call data in detecting the attacks or the anomalies that existed in our data set, at least. So I'm not saying this will apply to all kinds of data, because you have different types of attacks, some of those attacks could be more related to system call data, or they could be revealed more by system call data. But in our experiments, the network flow data was more effective in detecting those attacks. Well, I'd like to thank you all very much for your attention. And if you have any questions, I'd be glad to answer them.
Thank you, madam, for your valuable time spending with our students by sharing insights. Right? Now I request Shivkumar to propose the vote of thanks for this session.
Respected dignitaries, faculty members, and dear students, on behalf of the second International Conference on Mathematical Modeling and Computational Intelligence and General AI, CIGAI 2026, I extend our heartfelt vote of thanks, esteemed invited speaker, Dr. Pelin ANGIN, for delivering an enlightening and thoughtful session. Your expertise, insightful perspectiveness, and engaging presentation have greatly enriched our understanding of the topic. The practical examples, actual experiences have inspired our students and faculty alike. We truly appreciate the time and effort you have taken to be with us despite your busy schedule. We are also grateful to the management, principal, team, faculty members, organizing team, and all the participants for their wholehearted support and active participation, which made this session a grand success. Once again, we express our sincere gratitude to Dr. Pelin ANGIN for her valuable contribution and to to have the privilege of seeing that again in the future. Thank you all.
Thank you very much.
Thank you.
Thank you.